Hello, and welcome to Chapter 4, Section 2. Today we are talking about binomial distributions. So last time we talked about random variables and probability distributions. So today we're talking about a specific type of probability distribution. So it's like this certain scenario where we would use these formulas. So binomial is what it's called. Binomial meaning like if you've heard about uh, binary where the language is all in zeros and ones. So binomial just means that there's like two things. For us, binomial we'll talk about like either a success or a failure. So when we talk about binomial distributions or binomial situations, there's basically four rules. So the first one is I tried to make, an acronym to make it stand for something. So the first one starts with B, stands for binary. So everything is either a success or failure. The second rule is that you have to have independent trials. So when we do something the first time versus the next time that we do it, those two times that we do the thing has to be independent of each other. So whether I did it a success or a failure on the first time shouldn't affect whether the second time is a success or failure versus the third time, fourth time, however many times. The next rule is that there have to be n trials. So I'm using n to stand for a number. Basically, like how many times total are you doing something? So when I say like how many trials, that's how many times you're doing it. So n just means like you're going to be given how many times you're actually doing something. So it needs to be given to you in the problem. And the last rule is that you have to have the same probability of success for each trial. So basically, this goes hand in hand with the independent trials. So for each trial that you do, or each time that you do something, since they have to be independent of the next time that you do it, the probability of success shouldn't be changing because they are independent events. So each time you do something, the probability of success, whatever your success counts as, has to be the same. And so I made the four rules stand for bins, like because binomial, bins, whatever way to help you remember is what I'm going for here. So with our binomial probabilities, these are how you tell like when you should be using our binomial formulas, because in the next section we're going to learn more formulas for different situations. And so those situations have different rules. These are the four that we're starting out with. So our first thing that we want to be able to do is just recognize when we need to use binomial formulas. Because as we learn more formulas, then we have to be able to tell the difference, like, oh, when do I use this one? When do I use this one? So for right now, I just want to make sure that we can actually identify the different parts to our problems. And a lot of this is just like careful reading. So like a lot of information it should be given to you in the problem. So you just have to read carefully to see what type of situation we're talking about here. So there's a few symbols that I want to look at first because these symbols will help us use the actual formulas. So for these next few examples, we're not actually like calculating anything yet. We just want to be able to identify like, is this actually binomial? What would all the different symbols be so that when we are asked to find a probability, then we know what to plug in. All right, so the four things that we want to be able to find would be N, P, Q, and X. So N we talked about already. N stands for the total number of trials. So how many times total are you doing something in this problem? P is going to stand for the probability of success. So whatever you're counting as a success in the question, that's what you're looking for the probability of for just one trial for P. Q stands for the probability of failure. So once you have P, you just do 1 minus whatever P is to find Q. So because success, the opposite is failure, so opposites, we just do 1 minus whatever the probability is. And then lastly, X is how many successes are they asking for in the question? So that's going to change depending on the question itself. And then as we go through, sometimes it's going to be like less than this number, greater than this number, and then we'll have to start reading those as well. So here we go. First example, a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So notice here in this problem, they're not actually asking for a probability yet. So we're not trying to calculate anything. We're just trying to decide whether the experiment is a binomial experiment. So does it follow those four rules of binary, independent trials? Is there a certain number of trials? And then the same probability of success for each trial. And then once we decide that, then we have to specify what N, P, Q, and X are. Or no, just N, P, Q. because we don't have a question. And then it says list the possible values of the random variable x. So what numbers could x be if they were to ask? So here, first we need to define whether this is binary. So do we have something that's like either a success or a failure? Which yes, because they asked about these surgeries. You either have a successful surgery or a not successful surgery, which is not as good. But they told us it's an 85% chance of success. So we have our probability right there. We know it's success or failure. So that meets that binary rule. It also meets the same probability of success for each trial rule, which is the fourth one. We also need to check for independent trials. So we need to make sure that like from surgery to surgery, like after the first one that they do, the second one, all the way through the eighth one, that probability of success should stay the same. They haven't told us otherwise, so this should be fine. The only chance that it would be like not independent trials is if you remember like independent and dependent events. Dependent was where like you would pick something out of a hat or whatever, but then you wouldn't put it back. So that whole like lack of replacement, that makes things dependent and not independent. So that would be a case where it's like, oh, better be careful. It's not going to be independent trials. And then the third rule that we need to make sure that we have is that there are a fixed number of trials in this problem. So the total number of times we're doing something here is 8. It says a doctor performs the procedure on 8 patients. So we're looking at a total of 8 surgeries, and that's it. No more, no less. So because it meets all 4 rules of a binomial experiment, this is binomial. Now that we know it's binomial, then we just need to identify what N, P, and Q stand for in this problem. So N, remember, is our total number of trials, how many times total we do something here. So here we talk about 8 patients total. So N is going to be the number 8. P stands for the probability of success. So they told us the probability of a successful surgery was 85%. So P for us is going to be 0.85. So just a reminder, turn your percents into decimals, easy peasy. And then Q is going to be the probability of failure. So in order to find that, we always do 1 minus P. So 1 minus P of 0.85 will give us 0.15. So that's our probability of failure, 15% chance of failure. All right, then our last thing to do is list the possible values of the random variable x. So they're basically asking like, what could the question ask about for in terms of probabilities? So like, what is the probability of getting all 8 surgeries to be successful? Or what is the probability of having only 7 successful surgeries, or 6 or 5? And so we just want to list all those out. So we're going to say x could be any number from 0, because you could have 0 successful surgeries, all the way up to, and then the maximum would be 8, because you're only doing 8 surgeries total, so it doesn't make sense to have any more than 8 successes. Okay, so they're just asking what are all the possible values of the random variable x. So really they could ask about any number between 0 through 8. And so that's kind of in general, like binomial experiments, the smallest number is always going to be 0, because it's very possible that you have 0 successes. And then the biggest number is always going to be whatever your n is. That's going to be the maximum number of successes that you could have. All right, so we've done everything that we needed to for that first example. Second example, we have a jar that contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Okay, so here, because they're asking about a random variable represents the number of red marbles, what we're counting as a success then is drawing a red marble. So failure would be anything that's not red, so we're green. So we have success or failures for the first rule of binary. The second rule is that we need independent trials. But we just talked about if you're pulling things out without replacement, if you're not putting them back in, the probability of you drawing a red the second time, because there's less items total inside the jar or whatever now, that makes it dependent because you have different numbers in there now. So the second time you pull something out, the probability will change. So you don't have independent trials, the probability of success is not going to be the same now. So that was the second and fourth rules that this broke. So this is not a binomial experiment. So that first thing where it asks is decide whether the experiment is a binomial experiment. This is a no. If it's a no, we can't identify anything else. So we're done here. So now that we know how to identify whether this is a binomial situation or not, now we can actually go ahead and calculate probabilities. So the probability formula looks like this. We're going to have the probability of x equals, and then here I'm going to use like, this is kind of weird. The big X is going to be like, in general, this is like what the question's asking for. X, little lowercase x, is going to be like whatever number the question's actually asking about. So don't worry too much about that notation. I just needed variables. Okay. So the first part of our formula looks at the kind of like, if you remember the combinations and permutations we did last chapter, we're only going to use combinations here. So it's not like you have to decide which one you're going to use. But the part of the formula is that we're looking at combinations because when we ask about a certain number of successes for our probabilities, there's like different orders that you can do this in. And so the combinations, that's where it comes into play. Then we multiply that by the probability of success raised to the x power. So this is basically saying like, how many successes do you want? And this is asked about in the question. And you multiply that many times for your probability of success. Then you're going to take your probability of failure and raise it to the n minus x power. That's like saying out of however many total things that you're doing, want a certain number of successes, so that means the rest of them have to be failures. That's all we're doing here. So let's use examples then to actually try out this formula. So microfracture knee surgery has a 75% chance of success on patients with degenerative knees. So the surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. Okay, so going through this problem, remember if it's binomial, we want to be able to identify n, p, q, and x. So really quickly, n is like the total number of times we're doing the surgery. And it says the surgery is performed on 3 patients. So keep in mind, like, number should always be the biggest number because it's like the total amount. P is our next thing that we want to identify. P is the probability of success. They told us a successful surgery is 75% chance. So P is going to be 0.75. Q then would be 1 minus P, which will be 0.25. So 25% chance of failing. And then X, the number that they're asking about. It says find the probability of the surgery being successful on exactly 2 patients. So this is going to be 2 here. Okay, so using my formula, this is what it's going to look like. And this is why like that capital X and lowercase x is whatever, just go with it. So we have the probability that our random variable x equals 2. So following the formula, we have our n is 3, so we're doing 3C2 here because out of the 3 total surgeries that we're looking at, we want 2 of them to be successful. We're going to multiply that by our probability of success, which is 0.75, and we want 2 successes, which means the failures, if there's 3 total, 2 successes, that means 1 of them has to be a failure. So 3 minus 2 would give us 1 failure. Okay, so hopefully you remember in your calculator how to get to the 3C2. If you don't, we're going to type in the 3 first, go to Math, scroll to the right until you have PRB highlighted, and then it's number 3. So 3 says NCR, that's the one we want. And then our second number is 2. So we know 3C2 is going to be the number 3. And then we can multiply that by the 0.75 raised to the second power times 0.25 raised to the first power. So 3 times, let's do this with parentheses here, 0.75 squared times 0.25 raised to the first power, which is just 0.25. Okay, So our probability ends up being 0.4219, I think, if we round correctly, because the fifth number is a 7, so that rounds the 8 up to a 9. Okay, so in general for our probabilities here, I think most of the time it's going to ask you for 4 decimal places, so just get used to that. Okay, so finding that probability, not too bad. I want to show you another way that you can do it in the calculator, though, in the graphing calculator. If you don't have a graphing calculator, it's not as cool because you won't be able to do it this way. But I kind of think of it as a shortcut because there's less things to type. So instead of doing all of that, like writing it out and then doing it, we can go into second and then the vars button. So once you're there, if you scroll up, actually like way at the bottom of the list, but if you scroll up, then it'll get there faster. You look for Binom PDF. So Binom stands for our binomial experiments. PDF, and because there's a PDF and then there's a CDF. I'll show you how to use both, but for right now, choose PDF. So it'll ask you for how many trials do you want? And we have 3, because 3 was our N, so N trials. P stands for our probability of success, which is the same thing that we have. So our probability of success was 0.75. And then our X value that we were asked about in the question was 2. They don't ask you for Q because your calculator is smart and knows it can calculate Q on its own. So it'll only ask you for the probability of success, which is kind of nice. Less things to type. So hit paste because it'll just enter it in for you. If you don't have the updated calculator, it'll just give you Binom PDF and then it'll give you a parentheses and then you just type in these numbers on your own. So it always goes in the order NPX. So as long as you type those numbers in that order with comma separating each number, you'll be able to calculate this still. Hit enter, we get the same probability. Yay! So slightly faster, I think. My next example is going to be similar. So this time it says, find the probability of the surgery being successful on at least 2 patients. So at least 2, if you think about what at least means we want 2 or more. So this time, so I've written it out this way. If we want at least 2 patients, that means I want 2 or 3 successes. So remember our maximum number here of successes that we can get is 3 because we're only doing this a total of 3 times. So if we're doing greater than or equal to 2, then 2 patients or 2 successful surgeries or 3 successful surgeries. So if we find those 2 probabilities and add them together, that'll give us the probability of at least 2. So we can do what we just did with the Binom PDF twice. So the first time we're going to look for when x equals 2 as our x value, and then we'll figure out what it is for x equals 3. Those 2 probabilities, we can add them together. Since that last problem, we already figured out when x equals 2 what the probability was. We don't have to find it again. So for x equals 2, it was 0.4219. So if we just figure out the probability for x equals 3, that'll give us the probability to add to that. So second vars again, scroll up until I see Binom PDF. So again, I have 3 trials. The probability of success is 0.75, but this time I want x equals 3. So change that, enter. Oh, awkward. It's the same probability again. So this doesn't always happen. It just so happens for this problem that the probabilities for x equals 2 and x equals 3 are exactly the same. So 0.4219 again. When I add those together, I end up with 0.8438. So for this problem, it actually ended up being pretty easy to just add the 2 numbers together. But let's say, for example, another problem where instead of just having 3 total surgeries, we had like 10. So if you had a whole bunch of things that you would need to add together, this would be annoying to do because if you're looking for like at least 2 successes out of 10 total, that means you're finding the probability of 2, of 3, of 4, all the way up until 10, and then adding all those together would just get really annoying. So if that's the case, a faster way to do this would actually be to use the Binom CDF in your calculator. So let me show you how you use that. So second vars, scroll up again. This time, instead of PDF, we're going to use CDF. So C in CDF stands for cumulative. It means your calculator is going to add stuff up for you, which is kind of cool because it saves us time. So let's say instead we had 10 trials. So I'm just making up numbers here. 10 trials, we'll pretend the probability of success is still 0.75. Our X value, though, whatever we type in, our calculator is going to add up all the X values starting from 0 all the way up to whatever I type in. So if I typed in 2 here, that means my calculator is going to calculate the probabilities for X equals 0, because that's the smallest number that it can start at. So it'll calculate X equals 0, calculate X equals 1, and X equals 2, because it calculates up until whatever number I type. And then it'll find those three numbers, add them together, and then that would be the answer that it shows me. So for a problem where I'm looking for the probability that X is at least 2 means I want my numbers from 2 all the way up until the maximum, which if it's 10, then it would be from 2 to 10. And that really means I just don't want 0 and 1, because if I want the numbers from 2 to 10 added up, the only numbers I don't want are 0 and 1. So here, if I use binom CDF, I'm going to change this to 1 so that the calculator only adds up 0 and 1 for me. So this right here, it looks kind of crazy because I have an E in it. This is just scientific notation. So they're just saying this is like a really, really small number. Scientific notation means move your decimal place 5 places to the left because it's negative. So this would be like 0.000029556, whatever. So really small probability. But because this is the probability for X values of 0 and 1, these are the numbers I don't want, because if I want like at least 2, that means I want 2 through 10 and not the 0 and the 1. So if I do 1 minus this number, then this right here will be the probability for X values of 2 through 10. So 0.9999. Almost 1 basically. So really good probability here. But this is how you use the binom CDF. So depending on the problem, if it's asking for like from 0 up to whatever number, then you can just straight up do binom CDF. If it's like a greater than problem, then you're going to have to do the 1 minus first. The last part of this section then, if you think back to our first section, we talked about how to find the mean and standard deviation of a probability distribution. And because binomial probabilities are just probability distributions, just slightly more specific, we have better formulas for the mean and standard deviation of binomial distributions. So to find the mean, super simple formula, take your n, multiply by p, done. For the standard deviation, you're just going to take the square root of n, p, q. All 3 of those numbers multiplied together, and then square root the whole thing. So that's kind of nice. Easier to use than the formulas that we did last section. So here, if we do an example together, find the mean and standard deviation of the number of successful surgeries on patients with degenerative knees performed on 3 patients if it has a 75% chance of success. So the mean, we would just multiply n, which is 3, times the probability of success, which is 0.75. So when I calculate that, I end up with 2.25. So this means, on average, because this is a mean, on average, if this doctor was to perform 3 surgeries, he would get 2.25 successes on average, which is not bad for a 75% chance of success. Obviously, in real life, you're hoping for a better chance of success than 75% for your surgeries, but whatever. But that's what this mean means. That's what this average talks about. So when you're calculating an average or a mean of a binomial distribution, you're saying like out of our total number of trials, this is how many successes we would get. When we find the standard deviation, we would do our n of 3 times our probability of success of 0.75 times our probability of failure, which is 0.25, and I end up with 0.75, which means on average, each of our number of trials that we do for whenever we do 3 surgeries at a time, we're going to be off by the mean by about 0.75. each time on average. Okay, so that's how we calculate the mean and the standard deviation. So for this section, when we calculate probabilities, read really carefully because you want to be able to figure out what's n, p, q, and x, and then be careful when you're calculating your probabilities that you use the right x value. That's it for this section. Thanks for watching. Bye.